conventional thermocouples. Take a look at this if you are interested. So why do we need temperature sensing in wearables? So, because we want to measure our body temperature. But the question here is, since we're doing wearables, the sensors are placed on the skin. You are measuring skin temperature. Skin temperature is useful, but it's not as useful as core body temperature. So we want to be able to know core body temperature, but we can only place our sensor on the skin. That's one question we need to address. How can we know core body temperature from measuring on the skin? So, okay, so we know our core body temperature is higher than our skin temperature. And why is that? Why skin temperature is lower?
Because it's touching the air and the air is colder.
Yeah, because we are losing heat to air. So air temperature is even lower. So how can we get core body temperature from skin temperature? So the idea here is that, we can measure air temperature so we can know how fast we are losing heat to air, how many degrees of temperature we are losing due to, heat loss to air. Then, we can add that amount of temperature back to our skin temperature. Then we get our core body temperature. And this relies on thermal modeling. So this is a wearable device with, for inferring core body temperature. It has two temperature sensors. There's a one that you place directly on the skin to measure your skin temperature. And this temperature sensor has the thermal insulation. This is a thermal insulation that separates the skin from air, so you can accurately measure skin temperature and without being impacted by air temperature. So the thermal insulation here is very important. Then on top of the thermal insulation, we have another temperature sensor that measures air temperature. So two sensors, skin temperature and air temperature. So then by thermal modeling, we can see, we have, temperature measured by the top sensor, which is air temperature. We also have the bottom sensor that measures your skin temperature. Based on these two strings of data, you can use thermal modeling to infer your core body temperature, and it matches pretty well with your actual core body temperature. So just to show you, this is the same principle, but a different look, a device with a different look. So this is actually your MA, mechanical acoustic sensing device, but it has two IMUs. This IMU1 that you place on the skin to measure your skin temperature. It has thermal insulation. This is the second IMU that measures, the IMU measures acceleration, but also temperature. A second IMU that measures your air temperature. So you will see, your IMU1, which measures your skin temperature, is about 32 degrees C, much lower than your core body temperature. There's a second IMU that measures your air temperature. Then by thermal modeling, you can compensate for, heat loss due to air conduction. Then you can, calibrate your skin temperature to get your core body temperature. And it matches pretty well with, an oral thermist. The oral thermist is the green trace here. And the dotted red line is your calibrated, core body temperature. They match very well. So this is the power of thermal modeling. Then I also want to show you another device, that is based on exactly the same sensing principle. Two temperature sensors, one that measures skin temperature and one that measures air temperature. You will see by calibration, your device can infer core body temperature, and it matches pretty well with the gold standard, which is called EPU. That's something measures your internal, a core body temperature. They match really well. So this is how we get core body temperature using wearables. We need two temperature sensors. All right, so This is about temperature sensing. So do we have questions before we move on to the next part?
On the previous slide, you referred to the temperature sensor as an IMU.
Oh, yeah.
I thought that was for the
Yes.
mechanoacoustic
Yeah.
sense.
So,
accelerometer.
yeah, that's right. Because, IMU is for measuring acceleration. Almost, I think, I have used many chips and almost all of them have a temperature sensor because, for example, the IMU measures acceleration and its performance shifts with temperature. So you often want to calibrate for the effect of temperature. So that's why these chips have, built-in temperature sensors as well. So they have, temperature sensing capability. Although their main function is measuring, acceleration. Oh, yeah.
Is that I think the blue line,
Yeah.
is that a faithful representation of body temperature over time? Like, does it have that much high frequency content? That's not like an artifact of measurement, like body temperatures can fluctuate that rapidly.
Oh, well, the blue line is the temperature you measured using your wearable, and you see it goes low when, during sleep and goes up, in the daytime.
That's only 0.5 degree Celsius,
Oh, true.
so it's not that much.
Yeah, it's really 0.5
Okay, so
Celsius.
the variation in it probably is a little bit of noise.
Well, I don't think this is noise. This is because when you sleep, you have lower temperature.
Okay.
Yeah, just a little bit lower.
And that graph is not comparing with another.
It is. So look at this gray line. This is your something called EPO. Based on the name, I think it's a device you can ingest to measure your internal body temperature.
Okay. Thank you.
Yeah. Okay. So next we are going to talk about thermal conductivity. So there are two methods, TPS and 3 omega. So TPS means transient plane source. And in TPS, we are using